The fundamental theorem of line integrals is a generalization of the fundamental theorem of calculus, and there is a lot of heavy-hitting concepts that go along with this theorem. And today I want to just give you like a symbolic treatment of this. I don't want to get too focused on all the different physical interpretations of this theorem, and just take a minute to just focus on the symbol pushing. Just like in a math class, how do you push the symbols around on the page in order to produce like the correct numerical answer? I want to start our conversation about the fundamental theorem of line integrals by bouncing back to Calc 1 and talking about the fundamental theorem of calculus. So like always, when you want to understand something in Calc 3, look back at how it worked in Calc 1. So I want to just remind you of this object, the differential operator. We call it ddx, and what it is, it's an operation. So it's some kind of thing that takes a function and it does math to it, and then it spits out another function. So we think of it as an object, and the input of that object is some function. And what does this thing do to that function? It takes the derivative of whatever goes in front of it. In this setup, I'm imagining a situation where I have like y is equal to f of x. And then all I've done is I've just applied this differential operator to both sides of this. So you can really see it happening, right? If I started with like y is equal to f of x, then what I've done here is just like literally take the differential operator. I've just applied the differential operator to both sides of this equation. Okay, and so then for this one right here, this is what we usually call Leibniz notation, and it really makes sense. I mean, when you just like, if you want to just be abusive about the symbols, that is how we multiply fractions, but that's not really what's going on here. This thing is really just shorthand. Well, I guess really this thing is shorthand notation for that thing. And then the last one here, this is actually a statement about differentials. This is a way of saying I can approximate the change in y by calculating f prime of x dx. So, loosely speaking, these are just three different ways to look at the same relationship. Basically, I just started with y equals f of x, and then I applied the differential operator to both sides. And now I want to plug this into the fundamental theorem of calculus and see the different ways that can look. These are a bunch of different ways of writing the same thing. I think that this one right here, this is probably what you're most used to thinking of as the differential or the fundamental theorem of calculus. Usually if you have like 0 to 1 of like 2x dx, right? So there's the derivative. What you're going to do is x squared evaluated from 0 to 1. So there's the original function. So this is like our usual way of writing the fundamental theorem of calculus. And I want to look at basically all the different ways. So let's start over here, okay? And this really is the way, this one over here, this is really the one that is going to look most like the fundamental theorem of line integrals. So you can see here, basically what I've done is I have just taken the derivative of y. Well, so I've applied the derivative operator to y. So I have d dx of f of x. So hopefully you can see that these symbols right there are the same thing as that f prime of x. Okay, and then so dy dx is f prime of x. So hopefully you can see that these symbols right there go with those symbols right there. And then also dy is f prime of x dx. So hopefully you can see that those symbols right there do match with that symbol right there. So here's just a bunch of different interpretations of the fundamental theorem of calculus in a different way to write our very familiar process, of taking an antiderivative and then plugging in the endpoints. So fantastic. These are a bunch of different ways of writing the same thing. I especially want to focus on these two parts of it here, and I think when I write down the fundamental theorem of line integrals, you'll really see the similarity. But I have the fundamental theorem of line integrals written here, and this is really just a time where it is very, very transparent that the gradient is doing the same job that the derivative used to do. So let's just on a purely symbolic level, let's just match up the symbols in the fundamental theorem of calculus with the symbols in the fundamental theorem of line integrals. All right, so first of all, here I have the differential operator. That means take the derivative of, and you can see, boom, there it is, right there it is, replaced with the gradient symbol. All right, the rest of this pretty much matches perfectly. So there's a function, there's a function. All right, now for the differential at the end there, so in Calc 1, the path was always just restricted to the x-axis. So all we were doing was just like moving down along the path. So what was a small change along the path? It was dx. Now we have the path just has more freedom than it can move in, right? So now the path can go wherever it wants. And dr is just going to represent some small step along the path. So really, symbolically, dx does really match very well with dr. Okay, and then now these guys, that's just like literally the same symbols. Okay, so, from this point of view, the fundamental theorem of line integrals really looks like a generalization of the fundamental theorem of calculus. I mean, just symbol for symbol, they just match right up. So it just all slots right in, just all the pieces, all the dominoes just fall right into place, right where they're supposed to go, okay? In 3 dimensions, the gradient is partial x derivative, partial y derivative, partial z derivative. In 2 dimensions, the gradient is partial x derivative, partial y derivative. In 1 dimension, so the gradient should be a vector, but there's only one variable in 1 dimension, x, so the gradient has to just be d dx. So I mean, if you want to make the fundamental theorem of calculus look even more like the fundamental theorem of line integrals, this is totally legit. You could just put a gradient there, and then these symbols are just literally exactly the same as those symbols right there. So hopefully I've convinced you that symbolically, this is really nothing new. The fundamental theorem of line integrals is a very familiar thing. Every time you've been doing an antiderivative all throughout, and plug in the endpoints, every time you've calculated an integral all throughout your calculus career, you have basically been doing the fundamental theorem of line integrals. Okay, I'm gonna do one that's like maybe even too simple. I don't mean to insult you with this, but I'm just really trying to drive home this connection that this is what we've already done. So I'm gonna work out this simple integral problem, and this is actually the fundamental theorem of line integrals in 1 dimension. So what I'm gonna do is I'm gonna parameterize the path here. So my parameterization, I'm going to choose final minus initial times t plus initial. So I'm going to choose x equals t, and then t is going to be between 0 and 1. Okay, and so then when I calculate the gradient of f, what I'm going to do is the vector differential operator d dx of x squared, and what I'm going to get is the vector 2x. Okay, now in this problem, r of t is equal to the vector t. So when I calculate dr, I'm going to get the vector, the derivative of t is 1 dt. And so when I set up this integral, I'm going to do the integral from t equals 0 to t equals 1 of grad f, so that's going to be 2x, dot product with the vector 1, wait a minute, except x is equal to t. So here I don't have 2x, I have 2t, dot product with 1 dt. And the way that you do dot products is you multiply the coordinates and you add them all. There's only one coordinate. So here I get the integral from 0 to 1 of 2t dt. And so that's going to be, now I am literally using the fundamental theorem of calculus, t squared evaluated from 0 to 1, and you get 1. Okay, so, this is the most complicated way ever to work out this integral, 2x dx. But here, what I wanted to do is I just wanted to show you the kind of Calc 3 solution to a Calc 1 problem. Okay, so now let's do a proper Calc 3 problem. Here I am, the way that I did this solution right here is this is the by hand method. This is the brute force way to solve this problem. I am finding a parameterization and just churning through the objects and spitting it out. If I wanted to solve this problem using the fundamental theorem of line integrals, what I could do is when I calculated the integral of the gradient of f dot dr, what I could do is just f of b minus f of a. So the fundamental theorem of line integrals lets me skip all of this, and all I'm going to do is f of b, that's 1, minus f of 0, that's f of 0 here. So I'm just going to do 1 squared minus 0 squared, and I get 1. Okay, so the point that I'm trying to make with this is that there's two ways to solve all of these problems. This way here is you parameterize the path, you plug everything in, you calculate that dot product, you turn everything into t's, and then you spit out the answer. The fundamental theorem of line integrals is kind of like the shortcut way, where all you do is you just sort of find what your original function is the gradient of, and you just plug the endpoints in order to get the answer. Okay, so now I really am going to do like a Calc 3 version of this problem, and I'm going to solve it in both ways. Once the parameterization way, and once the actual fundamental theorem of line integrals way. Okay, so now a very similar problem, except now it's actually a proper Calc 3 problem. So here what I have is I have a vector field that is the gradient of x cubed times y squared. Then C is going to be this straight line path from one point to the other point. Just be careful, if you're in my class, I'm looking at the online homework, and they don't, it isn't quite this simple. I have a straight line path in the homework. It kind of like makes a letter L shape. So like, don't like just copy and paste the work that I do here. Actually read the problem and work it out. I trust you guys can do this. So I'm going to solve this problem in two ways. One way I'm going to do the parameterization way, and then the other way I'm going to do the fundamental theorem of line integrals way. Okay, so I'm just churning through this process. First of all, I figured out what capital F was. So, I mean, capital F is the gradient of this. So all I did was I took the x partial derivative and put it right there, the y partial derivative and put it right there. Okay, brilliant. And now the next thing I had to do was I had to parameterize this line. So this is the straight line path from 0, 0 to negative 3, 3. So all I'm doing here is like final minus initial times t plus initial. So I got this for my parameterization, and that gave me that r of t. So actually I can calculate dr. So I just need to just jump forwards and start doing these next little steps. Okay, so what I did next is here's my r of t that came from the parameterization. So all I did was take derivatives to get that. And now I'm going to need to plug everything into this dot product. Okay, everything's just rolling along pretty smooth. So what I have is 3x squared y squared. So I'm literally just taking that formula for x and plugging it in for x, and taking that formula for y and plugging it in for y, and that's what I got right here. And then it says f dot dr, so now I'm just doing a dot product with dr. So I'm just going to expand this dot product out, and it's going to give me an integral with a bunch of t's in it, and then I can just crank out that answer. It was super easy. I mean, this is like supposed to be the hard way. This one here wasn't actually so hard, but I mean, it was a lot of steps. So, you know, I mean, the way you do dot products is, you know, you just do this one times that one and this one times that one, and you add them together. So what I have here, there's a lot of powers of 3 in it, you know, and then just one quick antiderivative, and you got negative 243. So this here, we've done it doing a parameterization and cranking everything out, like turning it into a line integral and working out the answer. Now let me do it the fundamental theorem of line integrals way. All right, so that was a little bit easier. Let me walk you through this time. All right, so what does the fundamental theorem of line integrals say? It says that if you're trying to do a line integral of the gradient of some function, all you need to do is, oh, I have this set up wrong. This should be here, should be the integral from 0, 0 up to negative 3, 3. And all you need to do, if you want to figure out what that line integral is just plug those points into the original function and subtract them, just like the fundamental theorem of line integrals. And you can see that the theorem does check here. I mean, they can prove it, so it's always going to work. Yeah, so I mean, this is just a great thing. I mean, like, you know, on a purely symbolic level, one I mean, this is a bit cringe for me to say this, but one way to think of it is that, kind of the integral symbol and the gradient symbol cancel, and you just kind of plug in the endpoints right there. So I need to just talk about a little bit about the language that goes on with this, and something that's really wild about this process is when I did it this time, I had to use this straight line path, and then I got this answer. But when I solved it this way, nowhere in the problem did the path appear at any stage. So actually what this means is this answer I would have gotten no matter what, okay? So actually if I would have crossed this out and chosen some other path here, like maybe some parabola path or L-shaped path or triple curly Q or whatever, I still must have gotten negative 243. Whoa, so that is really crazy. So there's a couple of other concepts associated with this. I want to explain those concepts now. There are three important concepts that go along with the fundamental theorem of line integrals. And the first one is the idea of path independence. And this is an absolutely wild concept because most of the time, your line integrals do depend on the path. I mean, if you're calculating like a total mass, then yeah, it depends on the path. I mean, in general, if you're doing some amount of work, if you take a different path, it's going to be a different amount of work. And at some special times, it's independent of path. And this is a strange thing, and it's a fantastic thing. And any time that the fundamental theorem of line integrals applies, we do know that the integral doesn't depend on the path, because all you do is f of b minus f of a. It doesn't matter what the path is. This next one is kind of a big topic, but it's an important one. And this is the idea that line integrals represent the total change in height. That happens, and there should be like a link to a video on the screen right now where I explain what an exact differential form is. But right now I just want to make you aware of a simple way of understanding that is that your line integral represents some kind of total change in output value. And the last concept is that the vector field that you're dealing with has some kind of conservation of energy. So a lot of vector fields do have conservation of energy. It's a special thing. It's a rare thing. But in gravity, we have conservation of energy. Systems like springs have conservation of energy. So anytime there's kind of a closed system where no energy is being added or subtracted, that type of situation is when we have conservation of energy. We call them conservative vector fields. So when that happens, one of the things that we're seeing here is that happens exactly when your vector valued function is the gradient of some scalar valued function. A little fail at Photoshop there, I couldn't get the brush tool. So, this is kind of a rare thing to have your function be the gradient of some scalar function. And when that happens, this means that the scalar valued function must represent potential energy. So because of that, we're not going to call them antiderivatives anymore. We're now going to call them potential functions because they represent potential energy. And the big theoretical takeaway of the fundamental theorem of line integrals is that the fundamental theorem of line integrals says that these three phenomena must happen simultaneously. So anytime you're in a situation where you have path independence, that automatically means that your line integral is going to represent some kind of total change in output, and that happens exactly when the force field has conservation of energy, and that happens exactly when your vector valued function is the gradient of some scalar valued function, and the scalar valued function represents potential energy. So this theorem hits really hard theoretically. I mean, we are really taking three completely different concepts and marrying them together and saying that they all must happen at the same time. So this fundamental theorem of line integrals, I mean, on one point of view, it's kind of like, neat as a math problem, a kind of way to take difficult line integral problems and make them easy. You know, all you do is f of b minus f of a. And then theoretically, it says that these three seemingly very different things are actually, you know, just different versions of the same concept. So, you know, there's still a lot to talk about, and I have some other videos that are going to support this, but hopefully, you know, this is a nice introduction and you've at least got a kind of a symbolic take of what the fundamental theorem of calculus is really doing.